and those results in 3 dimensions and higher, well, you don't quite have the same results as you have in 2 dimensions. And so there's some reason to believe that the fact that unique continuation is not of the same nature in 3 dimensions actually makes this problem also of different nature in 3 dimensions. So it may very well be that Calderon's problem, if you were to formulate A and B anisotropic and only in L infinity, does not hold in 3 dimensions. Even though it has been proven to hold for, say, C11 functions or C2 functions. It may not be true all the way down to 1. There's a reason that may not be true. So that's why I didn't call it a conjecture, but rather it's problem, because it's not so obvious that that's actually true. But if it were true, then of course I'm in deep trouble here. Because then, when lambda A is equal to lambda 1, if you're hiding something that's isotropic, then A is entirely isotropic, and I just told you that A would then be equal to 1. And so you couldn't hide anything, because if they had the same Dirichlet-de-Neumann map, they had to be the same. And you couldn't make it the same Dirichlet-de-Neumann map with something different in it. So this instantly tells you, what does this tell you? It tells you that A cannot be isotropic. Well, I cannot control what you are hiding. That could be isotropic and anisotropic. So this means that I have to construct this to be anisotropic. So I have to make this object anisotropic. It has to conduct very differently in different directions. Otherwise, I couldn't make this technique work. Okay, so that's one thing. Now, let me then, since I did give me more time than I normally do, let me show you what happens if it's anisotropic. So just again, the Calderon problem. Could this, what happens to this kind of statement if you permit A and B to be anisotropic? What happens to this statement? Why is this statement not true? Because I claim lambda A is equal to lambda B doesn't imply that A is equal to B. And let's see what can happen. So let's see what happens. So we're going to do something that the geometers often do. We're going to change variables, or what's called the push forward. So how do you solve the Dirichlet problem? So basically here you have a coefficient that we call the coefficient sigma, grad u, grad v, grad u, grad u. And how, well, let's call it A, because that's what I'm called over there. I want to solve this problem here. How do I do that? I minimize this form here, subject to u on the boundary is equal to phi, right? And the minimizer here then gives me the integral of A grad u tilde, grad u tilde. That's a minimizer. That's how I solve the problem. There's a unique minimizer, and that's a solution just by minimizing the Dirichlet form. Now let's do the following thing, which is very simple. Let's say we have the domain omega here, and I have a similar version of domain omega here, and I take a mapping capital phi. So now this is x, this is y, so I take y is equal to phi of x. I change variables. And I do it in such a way that this domain is mapped to this domain. So I do it in such a way that phi of x is actually equal to the identity on the boundary. So any one point on the boundary is taken to itself. So on the boundary here, this point here is not taken to this point here, but it's taken down to that point there. It's not just that the boundary is mapped to the boundary, but the mapping is the identity. That's essential. And then inside, it's a C1 diffeomorphism. It's actually a Lipschitz diffeomorphism, because I just want to say that L infinity function. Now, if I do that, what happens to this Dirichlet integral here? So here it's an integral dx, let's say, because I'm over here. When I go over here, I can say this is actually becomes an integral of what? Well, what happens to grad x of u? Grad x of u becomes grad y of u, and then dy dx, right? Because that's a chain rule. Dy dx is d phi. That's the Jacobian of the transformation phi. Well, and the chain rule actually says it's a transpose of that, but that's just a matter of, you know, how you define d phi. So it's a transpose of this if you go down in x index and across and phi index. Okay? So now when you therefore calculate this, so you have this, so what you get is you get a d phi transpose, and then you have grad y of u. Then you have a grad y of u. This is grad x of u, so to speak, right? dx. Then you have grad y, and then I take the d phi transpose that I have here, I put it over here, d phi, because that's just transposition of it. And then I have dx here, but then I take dx dy and dy, right? And then dx dy, as everyone knows, is equal to dy dx when you divide by it. And dy dx is the determinant of this thing here with an absolute value. So the determinant of d phi, and now it doesn't matter whether you take the transpose, right? It's just the determinant of d phi. Okay, so what I just argued there is the following, that integral of a grad u, where this is x, dx, is equal to integral, and I'll call this phi star of a dy u dy. With phi star of a is equal to d phi a d phi transpose divided by the determinant of d phi. And then this, of course, all gets taken at x. It gets taken at x here, and x is phi minus 1 of y. So it's composed with phi minus 1, because I have to go back in x coordinates to pick it up. So this says that the Dirichlet energy of any function u is equal to the Dirichlet energy of that function u looked at it in y coordinates with this changed coefficient. This is called the push forward. That's really sort of a geometric construction. The push forward of the coefficient under this mapping phi. Now, if I minimize subject to u is equal to phi on the boundary, then I have u is equal to phi up here. What is u equal to on the boundary here? Well, since phi is the identity on the boundary, phi doesn't change on the boundary, it's the same function. So if I minimize subject to phi here, I minimize subject to phi here. So actually what you get is the minimum here is achieved the same place as the minimum here, just by looking at the function over in y coordinates. And since this thing here is just when you integrate by parts, this thing here is just equal to lambda a. You integrate by parts, you get divergence a grad u, that's 0. And then you get, on the boundary, you get the co-normal derivative, that's an LA of phi, integrated against phi. Well, what you get down here is you get integral of L phi star of a phi phi. And this is now an integral on the boundary. And since these two quadratic forms are the same, you now polarize them. The corresponding linear maps are the same. And so this says that the Dirichlet denominator map of A, the Dirichlet denominator map of phi star of A, where phi star is given by this, is the same. So now you see when you go out in the anisotropic category, there are a lot of matrices that have the same Dirichlet denominator map. You just take one, you construct any C1 diffeomorphism that preserves the boundary, and that corresponding coefficient, you haven't changed the Dirichlet integral, you haven't changed the boundary data. And so the Dirichlet denominator map is the same. Your observations on the boundary, or your observations outside this domain have not changed. And so that tells you that there is a high degree of non-uniqueness once you go to the anisotropic category. Then you can say, what does it mean if I'm down in the isotropic category? What does it mean? Because I know, so this is sort of a little exercise, I know that if I had two isotropic, so if A was isotropic and the push forward was isotropic, then they have to be the same, right? Because then the Dirichlet denominator maps are the same. So let's just do this. This is sort of a little exercise for the afternoon. It's actually not surprising, but let me just note the following. So phi star of A is equal to isotropic and A isotropic. Because we know that A has the same Dirac-Neumann data map as this, right? So if they are still sevens, both of them are still both isotropic. They have the same Dirac-Neumann data map and they are isotropic. Then phi star of A has to be equal to A. The only way phi star of A can be equal to A is if phi is the identity. So why is it that phi star of A is equal to isotropic and A is equal to isotropic? That implies that phi is the identity. It does it because you write down what you get out of this and you actually get that the mapping phi has to be conformal. And if it is conformal and it is at the same time the identity on the boundary, then it's the only possibility is the identity by Newton's theorem. In the two-dimensional case, what you get is that it's a Cauchy-Riemann equations. And so the Cauchy-Riemann equations with the same boundary data just gives you only the identity. So the isotropic category is very tight. There's not a lot of movement, but once you go out to the anisotropic category, there are all kinds of A's that could have the same Dirac-Neumann data, which makes this possible. So that makes this possible. On the other hand, it says I want to be able to do it for all A. I want to be able to have lambda is equal to lambda 1 for all A. What this sort of says, if the converse result is true, so what we've said here is that we've proven here that lambda phi star of A is equal to lambda A. Right? So that I have already proven. That's sort of just this change of variable that I made. Now you can ask yourself another question. I mean, there are many questions, but the natural question you could ask here is the following. Is it true that if